An ion source is a device that creates atomic and molecular ions. Ion sources are used to form ions for mass spectrometers, optical emission spectrometers, particle accelerators, ion implanters and ion engines. Electron ionization. Electron ionization is widely used in mass spectrometry, particularly for organic molecules. The gas-phase reaction producing electron ionization is where M is the atom of molecule being ionized, is the electron, and is the resulting ion. The electrons may be created by an arc discharge between a cathode and an anode. An electron beam ion source is used in atomic physics to produce highly charged ions by bombarding atoms with a powerful electron beam. Its principle of operation is shared by the electron beam ion trap. Electron capture ionization. Electron capture ionization is the ionization of a gas phase atom or molecule by attachment of an electron to create an ion of the form A-. The reaction is where the M over the arrow denotes that to conserve energy and momentum a third body is required. Electron capture can be used in conjunction with chemical ionization. An electron capture detector is used in some gas chromatography systems. Chemical ionization. Chemical ionization is a lower energy process than electron ionization because it involves ion-molecule reactions rather than electron removal. The lower energy yields less fragmentation, and usually a simpler spectrum. A typical CI spectrum has an easily identifiable molecular ion. In a CI experiment, ions are produced through the collision of the analyte with ions of a reagent gas in the ion source. Some common reagent gases include methane, ammonia, and isobutane. Inside the ion source, the reagent gas is present in large excess compared to the analyte. Electrons entering the source will preferentially ionize the reagent gas. The resultant collisions with other reagent gas molecules will create an ionization plasma. Positive and negative ions of the analyte are formed by reactions with this plasma. For example, protonation occurs by charge exchange ionization. Charge exchange ionization is a gas phase reaction between an ion and an atom or molecule in which the charge of the ion is transferred to the neutral species. Shimmy ionization. Shimmy ionization is the formation of an ion through the reaction of a gas phase atom or molecule with an atom or molecule in an excited state. Shimmy ionization can be represented by where G is the excited state species, and M is the species that is ionized by the loss of an electron to form the radical cation. Associative ionization. Associative ionization is a gas phase reaction in which two atoms or molecules interact to form a single product ion. One or both of the interacting species may have excess internal energy. For example, where species A with excess internal energy interacts with B to form the ion AB+. Penning ionization. Penning ionization is a form of shimmy ionization involving reactions between neutral atoms or molecules. The process is named after the Dutch physicist Frans Michel Penning, who first reported it in 1927. Penning ionization involves a reaction between a gas phase excited state atom or molecule G** and a target molecule M, resulting in the formation of a radical molecular cation M+, an electron E-, and a neutral gas molecule G. Penning ionization occurs when the target molecule has an ionization potential lower than the internal energy of the excited state atom or molecule. Associative Penning ionization can proceed via surface. Penning ionization refers to the interaction of the excited state gas with a bulk surface S, resulting in the release of an electron according to ion attachment. Ion attachment ionization is similar to chemical ionization in which a cation is attached to the analyte molecule in a reactive collision, where M is the analyte molecule, X+ is the cation and A is a non-reacting collision partner. In a radioactive ion source, a small piece of radioactive material, for instance 63 Ni or 241 Am, is used to ionize a gas. This is used in ionization smoke detectors and ion mobility spectrometers. Gas discharge ion sources. These ion sources use a plasma source or electric discharge to create ions. Inductively coupled plasma ions can be created in an inductively coupled plasma, which is a plasma source in which the energy is supplied by electrical currents which are produced by electromagnetic induction, that is, by time-varying magnetic fields. Microwave-induced plasma. Microwave-induced plasma ion sources are capable of exciting electrodeless gas discharges to create ions for trace element. Mass spectrometry. A microwave plasma is a type of plasma that has high-frequency electromagnetic radiation in the GHz range. It is capable of exciting electrodeless gas discharges. If applied in surface wave sustained mode, they are especially well suited to generate large area plasmas of high plasma density. If they are both in surface wave and resonator mode, they can exhibit a high degree of spatial localization. This allows to spatially separate the location of plasma generations from the location of surface processing. Such a separation may help reduce the negative effect that particles released from a process substrate may have on the plasma chemistry of the gas phase. Glow discharge ions can be created in an electric glow discharge. A glow discharge is a plasma formed by the passage of electric current through a low-pressure gas. It is created by applying a voltage between two metal electrodes in an evacuated chamber containing gas. When the voltage exceeds a certain value, called the striking voltage, the gas forms a plasma. A duoplasmatron is a type of glow discharge ion source that consists of a hot cathode or cold cathode that produces a plasma that is used to ionize a gas. Duoplasmatrons can produce positive or negative ions. Duoplasmatrons are used for secondary ion mass spectrometry, ion beam etching, and high-energy physics. Flowing afterglow. In a flowing afterglow, ions are formed in a flow of inert gas, typically helium or argon. Reagents are added downstream to create ion products and study reaction rates. Flowing afterglow mass spectrometry is used for trace gas analysis. Spark ionization. Electric spark ionization is used to produce gas phase ions from a solid sample. When incorporated with a mass spectrometer, the complete instrument is referred to as a spark ionization mass spectrometer or as a spark source mass spectrometer. A closed-drift ion source uses a radial magnetic field in an annular cavity in order to confine electrons for ionizing a gas. They are used for ion implantation and for space propulsion. Photoionization. Photoionization is the ionization process in which an ion is formed from the interaction of a photon with an atom or molecule. Multiphoton ionization. In multiphoton ionization, several photons of energy below the ionization threshold may actually combine their energies to ionize an atom. Resonance-enhanced multiphoton ionization is a form of MPI in which one or more of the photons accesses a bound transition that is resonant in the atom or molecule being ionized. Atmospheric pressure photoionization. Atmospheric pressure photoionization uses a source of photons, usually a vacuum UV lamp, to ionize the analyte with single photon ionization process. Analogous to other atmospheric pressure ion sources, a spray of solvent is heated to relatively high temperatures and sprayed with high flow rates of nitrogen for desolvation. The resulting aerosol is subjected to UV radiation to create ions. Atmospheric pressure laser ionization uses UV laser light sources to ionize the analyte via MPI. Desorption ionization. Field desorption. Field desorption refers to an ion source in which a high potential electric field is applied to an emitter with a sharp surface, such as a razor blade, or more commonly, a filament from which tiny whiskers have formed. This results in a very high electric field which can result in ionization of gaseous molecules of the analyte. Mass spectra produced by Phi have little or no fragmentation. They are dominated by molecular radical cations M+, and less often, protonated molecules. Particle bombardment, fast atom bombardment. Particle bombardment with atoms is called fast atom bombardment, and bombardment with atomic or molecular ions is called secondary ion mass spectrometry. Fission fragment ionization uses ionic or neutral atoms formed as a result of the nuclear fission of a suitable nuclide. For example, the californium isotope 252 Cf. In Fab, the analytes is mixed with a non-volatile chemical protection environment called a matrix and is bombarded under vacuum with a high-energy beam of atoms. The atoms are typically from an inert gas such as argon or xenon. Common matrices include glycerol, thioglycerol, 3-nitrobenzyl alcohol, 18-crown-6-ether, 2-nitrophenyloctyl ether, sulfolane, diethanolamine, and triethanolamine. This technique is similar to secondary ion mass spectrometry and plasma desorption mass spectrometry. Secondary ionization. Secondary ion mass spectrometry is used to analyze the composition of solid surfaces and thin films by sputtering the surface of the specimen with a focused primary ion beam and collecting and analyzing ejected secondary ions. The mass-charge ratios of these secondary ions are measured with a mass spectrometer to determine the elemental, isotopic, or molecular composition of the surface to a depth of 1 to 2 nanometers. In a liquid metal ion source, a metal is heated to the liquid state and provided at the end of a capillary or a needle. Then a Taylor cone is formed under the application of a strong electric field. As the cone's tip gets sharper, the electric field becomes stronger, until ions are produced by field evaporation. These ion sources are particularly used in ion implantation or in focused ion beam instruments. Plasma desorption ionization. Plasma desorption ionization mass spectrometry, also called fission fragment ionization, is a mass spectrometry technique in which ionization of material in a solid sample by bombarding it with ionic or neutral atoms formed as a result of the nuclear fission of a suitable nuclide, typically the californium isotope 252 Cf. Laser desorption ionization. Matrix-assisted laser desorption ionization is a soft ionization technique. The sample is mixed with a matrix material. The analyte molecules are also desorbed. The matrix is then thought to transfer proton to the analyte molecules, thus charging the analyte. Surface-assisted laser desorption ionization. Surface-assisted laser desorption ionization is a soft laser desorption technique used for analyzing biomolecules by mass spectrometry. In its first embodiment, it used graphite matrix. At present, laser desorption ionization methods using other inorganic matrices, such as nanomaterials, are often regarded as SALDI variants. A related method named ambient SALDI, which is a combination of conventional SALDI with ambient mass spectrometry incorporating the ion source, has also been demonstrated. Surface-enhanced laser desorption ionization. Surface-enhanced laser desorption ionization is a variant of MALDI that is used for the analysis of protein mixtures that uses a target modified to achieve biochemical affinity with the analyte compound. Desorption ionization on silicon. Desorption ionization on silicon refers to laser desorption ionization of a sample deposited on a porous silicon surface. Small source. A laser vaporization cluster source produces ions using a combination of laser desorption ionization and supersonic expansion. The Smalley source was developed by Richard Smalley at Rice University in the 1980s and was central to the discovery of fullerenes in 1985. Aerosol ionization. In aerosol mass spectrometry with time-of-flight analysis, micrometer-sized solid aerosol particles extracted from the atmosphere are simultaneously desorbed and ionized by a precisely timed laser pulses. They pass through the center of a time-of-flight ion extractor. Spray ionization. Spray ionization methods involve the formation of aerosol particles from a liquid solution and the formation of baryons after solvent evaporation. Solvent-assisted ionization is a method in which charged droplets are produced by introducing a solution containing analyte into a heated inlet tube of an atmospheric pressure ionization mass spectrometer. Just as in ESI, desolvation of the charged droplets produces multiply charged analyte ions. Volatile and non-volatile compounds are analyzed by psi, and high voltage is not required to achieve sensitivity comparable to ESI. Application of a voltage to the solution entering the hot inlet through a zero dead volume fitting connected to fused silica tubing produces ESI-like mass spectra, but with higher sensitivity. The inlet tube to the mass spectrometer becomes the ion source. Matrix-assisted ionization. Matrix-assisted ionization (MI) is similar to MALDI in sample preparation, but a laser is not required to convert analyte molecules included in a matrix compound into gas phase ions. In MI, analyte ions have charge states similar to electrospray ionization but obtained from a solid matrix rather than a solvent. No voltage or laser is required, but a laser can be used to obtain spatial resolution for imaging. Matrix analyte samples are ionized in the vacuum of a mass spectrometer and can be inserted into the vacuum through an atmospheric pressure inlet. Less volatile matrices such as 2,5-dihydroxybenzoic acid require a hot inlet tube to produce analyte ions by MI, but more volatile matrices such as 3-nitrobenzonitrile require no heat, voltage, or laser. Simply introducing the matrix analyte sample to the inlet aperture of an atmospheric pressure ionization mass spectrometer produces abundant ions. Compounds at least as large as bovine serum albumin, 66 kDa, can be ionized with this method. In this simple, low-cost and easy-to-use ionization method, the inlet to the mass spectrometer can be considered the ion source. Atmospheric pressure chemical ionization. Atmospheric pressure chemical ionization is a form of chemical ionization using a solvent spray at atmospheric pressure. A spray of solvent is heated to relatively high temperatures, sprayed with high flow rates of nitrogen, and the entire aerosol cloud is subjected to a corona discharge that creates ions with the evaporated solvent acting as the chemical ionization reagent gas. APCI is not as soft an ionization technique as ESI. Note that atmospheric pressure ionization should not be used as a synonym for APCI. Thermospray ionization. Thermospray ionization is a form of atmospheric pressure ionization in mass spectrometry. It transfers ions from the liquid phase to the gas phase for analysis. It is particularly useful in liquid chromatography mass spectrometry. Electrospray ionization. In electrospray ionization, a liquid is pushed through a very small, charged and usually metal, capillary. This liquid contains the substance to be studied, the analyte, dissolved in a large amount of solvent, which is usually much more volatile than the analyte. Volatile acids, bases or buffers are often added to this solution too. The analyte exists as an ion in solution either in its anion or cation form. Because like charges repel, the liquid pushes itself out of the capillary and forms an aerosol, a mist of small droplets about 10 micrometers across. The aerosol is at least partially produced by a process involving the formation of a Taylor cone and a jet from the tip of this cone. An uncharged carrier gas such as nitrogen is sometimes used to help nebulize the liquid and to help evaporate the neutral solvent in the droplets. As the solvent evaporates, the analyte molecules are forced closer together, repel each other and break up the droplets. This process is called Coulombic fission because it is driven by repulsive Coulombic forces between charged molecules. The process repeats until the analyte is free of solvent and is a baryon. The ions observed are created by the addition of a proton and denoted, or of another cation such as sodium ions, or the removal of a proton. Multiply charged ions such as are often observed. For large macromolecules, there can be many charge states, occurring with different frequencies. The charge can be as great as, for example, probe electrospray ionization. Probe electrospray ionization is a modified version of electrospray, where the capillary for sample solution transferring is replaced by a sharp-tipped solid needle with periodical motion. Contactless atmospheric pressure ionization. Contactless atmospheric pressure ionization is a technique used for analysis of liquid and solid samples by mass spectrometry. Contactless API can be operated without an additional electric power supply, gas supply, or syringe pump. Thus, the technique provides a facile means for analyzing chemical compounds by mass spectrometry at atmospheric pressure. Sonic spray ionization. Sonic spray ionization is a method for creating ions from a liquid solution, for example, a mixture of methanol and water. A pneumatic nebulizer is used to turn the solution into a supersonic spray of small droplets. Ions are formed when the solvent evaporates and the statistically unbalanced charge distribution on the droplets leads to a net charge, and complete desilvation results in the formation of ions. Sonic spray ionization has been coupled with high-performance liquid chromatography for the analysis of drugs. Oligonucleotides have been studied with this method. SSI has been used in a manner similar to desorption electrospray ionization for ambient ionization and has been coupled with thin-layer chromatography in this manner. Ultrasonication-assisted spray ionization. Ultrasonication-assisted spray ionization involves ionization through the application of ultrasound. Thermal ionization. Thermal ionization involves spraying vaporized neutral atoms onto a hot surface, from which the atoms re-evaporate in ionic form. To generate positive ions, the atomic species should have a low ionization energy, and the surface should have a high work function. This technique is most suitable for alkali atoms which have low ionization energies and are easily evaporated. To generate negative ions, the atomic species should have a high electron affinity, and the surface should have a low work function. This second approach is most suited for halogen atoms Cl, Br, I, at.